And the recording will be made available later. We'll put it out on YouTube and add the URL to it. Also, there's another recording that I made, by the way, last week where I talked to Wade about his astronomy equipment. And I think he went into more detail with it than what he'll do tonight. At least I sort of hope that's the case. But what I wanted to say is that if you're interested in more of a technical discussion of his equipment and how it works, make that URL available also. It's actually quite fascinating. Okay, I am going to mute everyone, but you will have the ability to unmute yourself if need be. And that's just so that if there are dogs barking in the background or something like that, it doesn't, you don't all of a sudden get the focus for the presentation. So I have got a slideshow here that I have put together. The way this is going to work is that Wade and I take a little bit different perspectives on astronomy, and that's typical. I think if you get two astronomers together, they're going to take the hobby in a little bit different directions. Wade is the astrophotographer. I'm absolutely not. So I'm going to be giving some background information on some of the objects that are visible in the sky if we had no cloud cover. And I'm particularly going to try to cover the types of objects that Wade has photographed. So hopefully by the time Wade tells you when it's a planetary nebula, for instance, you'll know what that means. Let's see, so I want to screen share here. And Wade, I am going to start the slideshow, and would you let me know if it's coming up full screen?
Okay.
Okay, so it's looking okay for everybody? Screen. You are?
Yes.
Okay. So we're going to talk about the night sky and what's available. And I put winter on here because, of course, the night sky looks different as you go from season to season and night to night. So if you can imagine with the sun in the middle and Earth out 93 million miles away, as we rotate once every 24 hours, we are pointed to the night sky in one location in winter that's different from summer or spring or fall. Because as we go around the sun and we rotate, we're actually looking at different parts of our galaxy. So these presentations have to change by season. And I wanted to briefly talk about the solar system itself. So this is what we usually all think of as the solar system. We've got the sun in the center. And by the way, the sun is responsible for 99.8% of the mass of the entire system. And you'll see as I go through this, the system is actually very large. So 0.2% makes up all the planets, plus what I'll mention a little bit later, the Kuiper belt and the Oort cloud. And if you look at this, let me get my screen arranged a little bit here. This is actually fairly accurate for the moment we're in that if you look closely to the lower right, you can see Jupiter and Saturn and Uranus and Neptune. And it sort of looks like they're unbalanced over in a way. Everything's over to the right side. And then Earth is in closer, and Mars and Mercury and so forth. Normally, these planets will be scattered all around the plane. And by the way, as we know, the planets are all basically in one plane. So think of it as almost like a record. The planets are in this one plane. The other parts of the solar system actually aren't constrained to that plane at all. And that the edge of the planetary part is really Neptune. Now, as we get out further, there's this area called the Kuiper belt. So you can see Neptune's right at the very start of where the Kuiper belt begins. And think of the Kuiper belt now not necessarily being completely within that plane. It's more of like a donut ring that's around the solar system. And Pluto is basically, it's out in that Kuiper belt. Pluto and another object that's just about the size of Pluto actually is Eris. These are largely icy bodies that are out there, and there's an incredible number of them. Thus far, I think we've discovered about 2,000 of them, but we think that there are a lot more. Outside of the Kuiper Belt, if you go out a tremendous distance, is a spherical shaped layer called the Oort cloud. Now, the Oort cloud is basically where our long period comets come from. So these are largely icy bodies, chunks of ice that have been there practically in a pristine state since the beginning of the solar system. So every once in a while, and by the way, this extends out so far, 50,000 what we call astronomical units. An astronomical unit, by the way, is the distance from the sun to the earth. You go out 50,000 astronomical units, you're about a quarter of the distance to the next star. So the solar system itself is really this whole thing, the inner planets, the Kuiper Belt, and the Oort cloud. That's really the whole thing is being held together by gravity from the sun. And of course, this system, this whole great big system, is moving around the center of the galaxy. So our solar system sits in the galaxy, and it's actually rotating around that galaxy. In fact, we think it's made about 28 revolutions around the galaxy. Every once in a while, something will come by. Maybe a star will come by and disturb the Oort belt, or the Oort cloud rather, a little bit. And one of these chunks of ice will have its position disturbed enough such that it will come in and get into the inner planets and go around the sun. And that's what forms a comet. That's why sometimes you'll hear that the comet that we're looking at has an orbital period of some incredible length of time. That's because it's coming such a distance. Okay, the night sky itself, if we just look up to the sky, this is the area that contains most of the objects that we're going to be talking about. And if you look at this, the reason I'm putting this up here is because we always show diagrams that show you the constellations that we're looking at. And so I wanted to show you what the sky would really look like. If we look to the lower right, you'll notice that Mars is basically, this is in the west, southwest. You'll be able to see that. If we had clear skies, you could go out and you'll see it. It's a pinkish, bright object out there. It does not twinkle for reasons I'll explain a little bit later. And then just a little bit from it is Uranus. Uranus, you're not going to be able to see unless you have some visual aid, because it's so much further away that it looks a lot smaller than Mars does. Then if we move further over to the left, we'll see some bright stars, but in particular, I want to concentrate around what I will tell you is the constellation Orion. Now, Orion's pretty easy to pick out, largely because of the 3 stars that form Orion's belt. They're nice and in a row. They're almost equal in luminosity, so they're just as bright as each other. This is the belt of Orion, and then there are some stars below the belt that are called the sword of Orion. There are 2 stars here that are very noticeable. The one at the upper left that looks pinkish here, that's Betelgeuse, or some people call it Betelgeuse. Those are both acceptable pronunciations. This star has been doing a very weird thing this last year. It's a variable star, which means its luminosity will go up and down. But this last year, it really started dimming. It dimmed down to about 1/3 of what its normal luminosity is. And astronomers started speculating that it was getting ready to explode. So that it was going to explode into a supernova sometime soon. And by the way, there are different time frames, right? When an astronomer says soon, you need to ask them what time period they're talking about. And in this case, they're talking within the next 1,000 years is when they think it might explode. Down in the lower right, by the way, you can see another star, Rigel, and notice its color is quite different. Now, the color of stars is a little bit of a tip-off to their surface temperature. So a blue-white star has a much hotter surface temperature than does a red star, like Betelgeuse. Now, if we actually take a look at the constellation itself, we're going to focus down on Orion a little bit here. So I've got a picture of it on the left, and then on the right, you can see the art figure. This is the Greek mythology figure of Orion, the warrior. And sometimes you see him with a shield out front. Sometimes you actually see him with a bow and arrow. And by the way, this is pointed toward another constellation called Taurus, which is Taurus the bull. But if the parts that I want to concentrate on with Orion is the star, of course, Betelgeuse in particular, I'm going to be talking a little bit about, but then also the part that you see where it says the Orion Nebula, and there's an arrow going down to the belt area, and in particular, that center star of, not the belt, rather the sword, that center, there's a huge, what I'm going to call a molecular cloud there. And this is what's called a star nursery. So this particular molecular cloud has stars that are forming in it. And it's about 1,300 light years away. It's one of the most studied areas in the sky because of what's going on there. We're very interested in how stars form. So been doing a lot of looking at this for, astronomers have been looking at this for a long time. It's easy to see. This nebulosity here, you can see it with the naked eye. It's a lot more obvious when you look at it through binoculars. And of course, it's a favorite telescope object. So here I've switched over and I took a picture with an app that I have on my phone. This is called Sky Safari. I'm going to talk a little bit about things that you can use to actually help learn the sky and learn what's up there and also get some information about it. I take this out every time I go out stargazing because I can click an object and bring up all the information all kinds of information that's been written about it, as well as knowing, how far away it is, how bright it is, but also what it actually is. So I like Sky Safari a lot. And there are other apps also that you can get, and a lot of them are free. So you can start, self-teaching. Also, I'd like to point out, if you look down, I assume you can all see my pointer here. I'm circling something called M42. M42 is a catalog number for the Orion Nebula, and I'm going to explain just a little bit about where those numbers and that designation came from. Before I do that, let's go back to Betelgeuse. So Betelgeuse is one huge, huge red giant star, and this is just a diagram trying to give you an idea of how large that star is. So the lower left, you excuse me, you see the sun, and then up from the sun is a large star in Taurus, actually, it's Aldebaran. Even larger than Aldebaran is Rigel. Remember, that's in the Orion constellation. Even much larger star is Antares. This is in the Scorpius constellation, which you see in the summer. And then you see Betelgeuse here on the upper right. So it gives you an idea of how much larger Betelgeuse is. Huge, huge star. If we had this star at the center of our solar system, the edge of it would extend out to about the orbit of Jupiter. So we would actually be inside of it somewhere. Now, there's a phrase here, it might sound kind of funny in the first place, fuzzies in the night sky. And it's a term, actually, believe it or not, astronomers use. They talk about going out looking at the fuzzies. And to understand what they're talking about, I thought I'd mention a couple of things here. Stars show as points of light. To the eye, there is no dimension to a star. It's a point. And they can twinkle. And astronomers don't like to see twinkling, by the way. It indicates instability in the atmosphere, which makes looking at an image through a telescope shaky. In fact, I'm sure Wade really doesn't like to see stars twinkling because it's going to disturb his photographs. Planets don't twinkle for the most part because planets are balls of light. So even though, they may be a long way away and appear very small, nonetheless, it's a ball of light. They're a lot closer to us and they don't twinkle. The fuzzies sort of look like very distant clouds in the sky, like light smears and so forth. And one of the things that can appear somewhat like a smear of light, of course, is a comet, such as Neowise. So that brings me to an astronomer, historic astronomer, Charles Messier. Lived in the 18th century, very famous astronomer. He was French. He was something like, I think, 10th of 12 children in his family. And he worked for a while for an astronomer for the French Navy, which is where he got a little bit of a background in astronomy. And he became interested in astronomy because apparently of a great six-tailed comet in 1744. So if you look down the lower right of the slide, you'll see there's a picture of Charles Messier, and then there's an artist's drawing of this comet that must have appeared in 1744. So it piqued his interest in astronomy, and Charles Messier became what's called a comet hunter. So comet hunters, they scan the sky with their telescopes, and they're looking for these fuzzies, because long before a comet gets to be as big as what you see in this picture down here, they will appear faint and small anywhere basically up in the sky. Comets do not simply live within that plane that's the planetary plane. They can come in from any direction from that Oort cloud sphere at the, that surrounds the solar system. It's actually part of the solar system. So comets are fuzzy, but the thing that distinguishes a comet is not just that it's fuzzy, but that it moves against the background stars, maybe not from night to night, but from week to week. So they don't stay in the same place. Now, planets do the same thing, right? Planets, they will sometimes be in one constellation and then they slowly move through the other constellations as they're going around in their orbit around the sun. But comets, or rather, planets don't look fuzzy. They don't look fuzzy at all, whereas comets do. And then, as of course, as the comet gets closer and closer in toward the sun and starts heating up more, they start gassing. The gases then start glowing. They start ionizing, and we can see then the tails to the comet. So they start looking fuzzy. So this guy by the name of Charles Messier was a comet hunter. And as he looked at these fuzzies, he was looking for fuzzies that move against the background stars. So he would think that this is a possibility for a comet. We should start looking at it. But that he noticed that there are some fuzzies out there that don't move against background stars. So therefore, they are not comets. So what he did is he created a catalog of these things, made a list of them, and he published this so other astronomers that were comet hunters could take a look at it and basically say, I know this thing there is not a comet. It kind of looks like one. It's a little bit fuzzy, but it's not a comet, so therefore I'm going to ignore it. Now, this was in the middle of the 18th century, and they didn't know that anything about galaxies or molecular clouds or star clusters, actually, all sorts of things. And it turns out that this catalog of objects that he made to be catalogs to ignore are some of the most interesting objects in the night sky. So it's typical for amateur astronomers, especially those beginning, to go through this catalog of 110 objects and try to find them. And we're going to be talking about some of them tonight. Okay, this is an example of one of those fuzzies. Right in the middle here, you see that thing that looks sort of like a cloud. That's what I would refer to as a molecular cloud. This is what the Orion Nebula is. So it's a cloud of gas, basically of hydrogen and helium, might have a few other metals in it, but it's largely, think of it as hydrogen. And this is a huge cloud. Like I said, it's about 1,300 light years away from us. There are many, by the way, molecular clouds. The Orion Nebula isn't the only one around. And within this cloud, stars can form. In fact, in the Orion Nebula, that's exactly what's happening. Now, think of this as like a pot of gravy that's being stirred and that has the ability to get lumpy. And those lumps will condense and basically become a stellar system. And that's exactly what happens. Once that process starts and this lump starts collapsing within this molecular cloud, typically it also starts rotating. There'll be some spin associated with it. There'll be a disk that's formed. Most of the mass will go into the center, and actually, eventually, when the gravitational pressure is high enough, the star will fire up. It will begin nuclear fusion, and basically it'll be fusing hydrogen and making helium, and in that process release energy. Now that will start, so that's the birthplace of a star. Now, stars have life cycles, so they come from places like this molecular cloud. Our sun must have come from one at one time, about 5 billion years ago. And there are basically two paths that a star will follow. It will either take the circle to the left or it will take the circle to the right. And which circle it takes depends on the mass of the star itself. So a star, and I'm going to use our sun as kind of the standard. Our sun, which is a solar mass of 1, starts fusing hydrogen into helium, releasing energy. It will continue burning this until it burns out of fuel. Once it starts really getting low on fuel, believe it or not, whoops, sorry about that, it will start to swell and become what's called a red giant. Betelgeuse is a bigger version of this. You can see over on the right side here, we also have a counterpart over there. But at that point, our sun will swell, and the estimates right now are that it will swell about out to the orbit of Earth. So at some point, Earth is going to pretty much get fried by this big red giant of a star. As it goes along, ours is big enough that once it's fused most of the hydrogen, it will probably start fusing helium then, and that will become the fuel for a while. The helium will fuse, become carbon and oxygen. And eventually, though, this is going to run out of fuel and start to collapse and start shedding layers, and will become something called a planetary nebula. Now, a planetary nebula typically winds up with a small star called a white dwarf in the very center of this. You can see the planetary nebula. It's not a planet at all, right? But it's larger and round and kind of looks like a planet, so they called it a planetary nebula. The size, by the way, of the white dwarf is about the size of Earth. So we expect our sun to eventually shrink down to about the size of Earth. And this will stay very, very hot, but it won't be fusing. That's not where it's getting its energy. It won't be fusing any elements to create other elements, but it'll stay hot for an incredible length of time, actually. And this clouds of gas that it's been shedding will just keep getting bigger and bigger and bigger until finally it's completely diffused and you just have the white dwarf. Now, if you're a larger, let's go back to the molecular cloud. If you're larger, and by larger, I mean 10 to 25, at least above 10 masses of the sun, you're not going to go this route. This is called, by the way, the main sequence route, the one going to the left. The other one is going to, if you're bigger, more massive star, you can see this is like a blue-white star, so it's going to burn very hot. And the rule in stars is that the hotter you burn, the shorter you live. So some of these massive stars, they only live millions of years, not billions of years like our sun has lived. So actually, a massive star isn't a good place to go look for life if life evolves the way we think, because you need to be around a star on a planet, not only that's the right distance from the star, but you also need to be around a star that's going to live long enough for life to evolve. So these massive stars, they're not as good a deal. At least this is the way our thinking goes these days. But they will burn up their fuel. They'll swell up, become a super giant, a red super giant, and then their next stage will be to collapse and explode. They will become a supernova. And there are two outcomes from becoming a supernova. You'll either form a neutron star or a black hole. And by the way, I'll put in my plug here. People think that falling into a black hole is a bad deal, which of course it would be, but these things aren't nearly as dangerous to the rest of the universe, from my way of thinking, as a neutron star is. These neutron stars are really scary objects. They're still in our universe. They haven't kind of ripped a hole in space like the black hole does. They can explode, and these things are incredible. Matter has been crushed in them. There are no such things as atoms. They're just neutrons together. They're incredibly dense, incredibly powerful. And we've got some examples of these. In fact, Wade is going to show, I believe in your list, you had the Crab Nebula, right? Crab Nebula has at the center of it has a neutron star. They're hard to see. They're very dim. This is about the size of a city. So they're even smaller than a white dwarf, but that's because matter itself has been crushed down into just neutrons. So these are the life cycles that stars go through, and it's either one path or the other. They start out in these nurseries of these molecular clouds. Okay, so Orion Nebula, we can see that this must be one that Messier discovered. It's got an M number by it, M42. So this was number 42 in his object list. It's glowing up here. So he's telling people this thing's glowing up there, but it's not moving against background stars. This is not a comet, so ignore it. Well, it turns out it's not a comet, but it's a star nursery. This is you can see that we're still looking at Orion. This is not the Orion Nebula, but this is showing that there are other gas clouds out there around the Orion constellation. It turns out around the Orion constellation, there's just a lot of action going on as far as molecular clouds is concerned. You see it in other places also. If you look a little bit to the west and north of Orion, you run into the Pleiades. Notice they also have an M number, M45. These are beautiful stars. This is also called the Seven Sisters, but you can see there's some luminosity happening around them. By the way, the luminosity, these nebulae that glow, they're not glowing on their own. What's happening is the big stars in them are emitting typically a lot of energy in the form of ultraviolet. And that ultraviolet is being absorbed by the molecular cloud and excited. They excite the atoms in there. And when those atoms fall back to their normal state, they release light. And that's what we see as the glow in the cloud itself. Not all clouds do this. Some clouds are quite dark, actually, particularly if they haven't got any big stars in them that are releasing this energy. So these fuzzy objects, they can be of several different varieties. The fuzzy objects can be galaxies. Andromeda is an example. Notice it's got an M number to it, M31. Molecular clouds like the Orion Nebula, it's got actually two M numbers with it, M42 and M43. Supernova remnants. Remember I was talking about neutron stars at the center of them? This is a supernova that's exploded and blown off all these layers, and they can be quite beautiful in the middle of them, like in the Crab Nebula, we've got this neutron star, or they can be planetary nebulae, again, another Messier number, where they are blowing off clouds of stuff, and we're going to wind up with a white dwarf in the center. And an example of that is one that I believe Wade also has in his pictures of the Dumbbell Nebula. So that brings us to Wade. So Wade and I have known each other for quite a while. I don't know, 12 years at least, I think. And Wade has taken his interest in astronomy in the direction of astrophotography. And I remember when Wade first started showing his photos, and I thought they were remarkable, actually. But I can tell you that the ones that I've seen of what he's been up to this last year, he has made quite a leap forward. So, on that note, Wade, I'm going to let you take over. So, I'll do the stop share here.
Okay. One of the things I want to mention before I start is that I'm using a DSLR for my camera because the one built into my computer was horrible. And but the drawback to it is that it keeps shutting off about every 15 minutes. Tomorrow, I will be getting a new camera, but that doesn't help me tonight. So anyways, kind of where I wanted to start was along the lines of showing a little bit of my observatory. The other day when I was giving it, this is my first real Zoom meeting, so I was kind of getting the hang of this. I shared a lot of pictures with him, and so it was a little bit challenging to narrow it down. So I'm sharing a smaller selection. If you see the video that Sandy is going to provide a link for at some point here, it will give a little more in-depth perspective on this. Now, is that showing it doesn't look like it's showing.
Oh, it's fine. I see it.
Oh, okay. I'm going to go, is it full screen now?
Yes, it's full screen.
Okay, so as soon as COVID hit, it took only about a couple of weeks for me to kind of go, you know what, I really need something to do. And I have had, for the duration of time that I've been without imaging equipment for the past 7 years, I have been using a large 16-inch Dobsonian just to do some general viewing in my yard mostly. And as much as I do love viewing, especially through that 16-inch, it really doesn't have the ability to capture the essence of what the deep space objects are. So I decided it was time, and I figured I had a budget of $500, which I totally blew out of the water. And so after some planning and a little help from a construction friend of mine, I managed to build this contraption out in my yard. As you can see, it's got a very short door. This is probably about maybe around 4 feet high. And that gives me the ability to have this top section slide off towards the left in the picture here. And I have another image that you can see here with it open. And you can see I've got this little opening right here that allows me, I have to open that first, and then the whole roof slides back. And also, just to make mention, down on the ground here, you see a wood pole with a wooden panel on there. And I wasn't going to mention anything about it, but I probably should, because sometimes when I'm imaging on a night when the moon is fairly bright, be it full or even, you know, any phase of the moon, it can create a glare on the insides of my telescope. And so sometimes I might just lean that up against the building, making a shadow over the scope, which only lasts for so long, but it does help. So this is probably the most important piece of my entire observatory. This is the Skywatcher EQ6R Pro mount. And what this does is it gives me this, in conjunction with the concrete pillar that it's sitting on, gives me the stability I need and the accuracy that I need to grab onto an object and hold it very steady for long periods of time. Sometimes that may be all night long. In fact, it's not uncommon for me to work on a single object over a series of nights. So I may grab 8 hours one night, 10 hours another night, just depends on how much light I have available and what I can grab with it. So if anybody's interested in astrophotography, a high quality equatorial mount is the first most valuable piece that you can get. Let's see here. Zoom out to this before I let me go forward. Okay, I didn't mean to go directly to this. Let me shift out of here just a little bit because I want to jumped right to this other stuff. I want to show you some more on the observatory itself first. So this is the same thing backed out just a little bit to give a little more of a view of the scopes. I have 3 telescopes on here. The orange one in the back is a 8-inch SCT, and that is particularly good for getting up really close for dim deep sky objects. And when I say dim, I probably mean very small is more like it. This black scope right here, which is an Orion Eon 72 millimeter, pretty small scope in the scheme of things. That scope I use for all of my larger objects, which the majority of which I'm going to show you in a little bit here, fall into that category. So, and then there's a little tiny scope right here that is the guide scope. And what that does is using software called PhD Guide, PhD referring to Push Here Dummy. It's very simple to operate, particularly once it's calibrated. But basically, when you get your telescope in the vicinity of what you're trying to image, you use the guide scope and you click on a star, and that camera right here, the red small camera, is looking at that object and deciding whether or not that object is staying still in the field of view. And if it moves at all, it shifts the mount to match that location where we originally had it. And it does that, it varies to what degree it does that, but it can do it up to 60 times a second. So it's very quick and very accurate with what it does. So moving on, there is another camera that is on this system, and it is right off the edge of the mount right here. And that camera is what allows this entire mount to be very accurately polar aligned. With equatorial mounts, you have to be polar aligned to Polaris roughly, but more exacting to the north axis of what is basically the Earth's spin. And that camera, using software, is capable of getting me accurate to an absolute pinpoint. I'm sure that there's observatories out there that can do it better than mine, but I've not ever been able to get it as good as I have with this camera. Normally you would use a polar finder scope, and they don't have even remotely the accuracy. So these are what's called Batinov masks. And these masks are placed in front of the telescope, the primary lens, and they put a pattern onto, I'm viewing everything that I'm doing on a video screen. And obviously without the Batinov mask, I'm seeing, the standard image that one would expect to see, albeit typically dim, with the exception of stars. But the goal here is to grab a bright star and get it centered and place this Batinov mask in front of the telescope. And it uses diffraction lines to put a pattern on the screen. And that pattern is in the form of an X. And that X will have a line going through the middle of it that is not part of the X. And if you focus in or out from that point, then that line will move up or down the X. And the goal is to get it centered right at the center point of the X. And when you do, you achieve perfect focus. And that is a necessary component to be able to do any of the things that I pull off. I actually did it for a long time without a Batinov mask, but as soon as I started using them, the difference was astounding. So, and you might notice it in some of my images. I really, only in the last few that I'll show you, did I actually use a Batinov mask. This is an electronic focuser. And this device basically connects to my focuser, in this case on my 72mm refractor. And this allows me, once I use the computer to achieve my focus points with this device. It is USB, and I'm able to save that focus point as a reference for the temperature that I'm dealing with, because as you go up and down in temperature, it affects the focus of an image. So I have logs that I keep that will give me a certain temperature. My general focus, and I say general for a specific reason, which is through my luminance filter, is going to be at a given number set. Then from there, I have actually several filters in my setup that all require a slightly different focus. And so my system knows, because I've calibrated it, that if I'm focusing at said number at luminance, that if I switch to red, it knows that it's up 220 steps. If I focus it, or if I switch to blue, it knows that it's down 179 steps, and so forth through all my filters. So this gives me the ability to completely automate my imaging process. Once I get my primary focus, all of my filters will automatically adjust focus according to the temperature and which filter. And again, this is the guide scope. I just wanted to get a close up on that. It's pretty small. The telescope itself is really this silver area, and it's a 30mm refractor. It's nothing special. It's quite inexpensive, and quite frankly, so is the camera itself. This setup right here is about $250 for the camera and the scope, but it's priceless in what it does for the imaging. This is my primary imager right here, and they get pretty fancy these days, but this one here is I like to think of it as an entry level into a high-end camera. This camera, along with the filter wheel setup that's attached above it, you can see it right here, which I'll show again in a moment, is about a $2,000 setup. It runs 16 megapixels, and it records specifically only in mono, so no color whatsoever. The color is decided by my filter wheel and how I classify those images in the later process. So if I'm imaging in red, typically a standard color image is going to be recorded, captured through 3 filters. It's going to be captured in red, green, and blue. And as you're all familiar with, as using computers go, or printers, there's typical channel, color channel configurations. And for astronomy, it's typically a 3-channel, which is RGB. And then in addition to RGB, we also capture hydrogen alpha, oxygen 3, and sulfur 2. And I don't know what the 3 or the 2 means on those. I just use the filters. But obviously, based on the names, it's oxygen and sulfur. But the most important one being hydrogen, because it is probably the most common gas in space that appears to be illuminated by its surrounding objects, as you will see from some of my images. Now, if we move on, this is the filter wheel here, and there are 7 filters that are in a circular carriage around this thing. And via the USB port here, the computer is completely in control of that. I tell the system that I want, we'll just say, for example, 20 images in red, 20 images in blue, and 20 images in green. And when I'm done with those images, I will do what's called stacking. And I will stack all my reds and my blues and my greens independently. And those images will average out all of the noise and the light that's in that image, and give me the best possible average between all of them. And typically, the more you capture, the better it is. You get more luminance by capturing more light, and continued noise reduction. And for one of the things that I do, noise reduction is probably one of the biggest things. So our effort of trying to capture down those light bands into individual bands, and then combining them later in, say, Photoshop or PixInsight or different softwares that I use that are very effective for the processing. Now, you'll have to pardon me here, I'm just gonna jump back through these for a moment because things got a little out of whack for my goal here.
Yeah, could I just jump in here a minute, Wade?
Yeah.
So what it amounts to is that I'm a visual observer. Wade is an astrophotographer. When you're looking at one of these objects, you don't see them with the naked eye. You don't see them in nearly enough detail because our eyes were built for really a different purpose. So if you think about when you're actually looking at an object, you've got light, the photons coming in, your retina is grabbing it real time and assembling an image in your brain. And it's being done in really a very, very short period of time. An astrophotographer is doing somewhat the same thing, but of course, think of them as staring at this object for many, many hours, collecting the light, and that's what gives the photographs the ability to see things in much, much more detail than what you would see if you were looking at it through a telescope with just your naked eye.
That is correct. And in fact, the detail that we're looking for is so faint, and most of the times you never see the detail until you're in the final stages of processing the information. Most of the time when I'm looking at raw data, I see a fuzzy probably that is very similar to what we would see looking with the naked eye through a telescope. So that's why also the focus is absolutely critical, because there's nothing worse than capturing all this data and finding out later that you've got big giant fuzzy stars when they're really supposed to be pinpoints. And some of these, this particular group I'm going to show you is the ones that I am probably most excited with. This was my first deep space object with my new camera. And I got this object, I want to say I think it was in July. And this is Andromeda M31. So it is a Messier object, as Sandy was speaking to earlier. This is also our closest neighboring galaxy. It is believed to be a similar type of spiral galaxy as we exist in, although it is dramatically larger and heading our way. So this is a moderately easy object to capture. The challenge is that the center is real easy to blow out, and then which then stops you from getting your faint cloud base out here on the edges. So this was more or less a test for me, and I felt really good about the results. So this one was a much more difficult target, also taken early on, and is, if I zoom in on it here, this is called the Bubble Nebula. And this is NGC 7635. It is located near Cassiopeia, and it is a, hold on, my camera just went off again. Give me 1 second. It is, I'm not entirely sure what created this. All I know is that it is a beautiful image, and my camera's trying to import pictures. Let me stop it. All right. Anyway, so to me, it's just an interesting image that I was able to reach out and capture. I admired other people's versions of it, and so this was my shot. In the future, I plan on taking that same image with my orange telescope, my SCT, because it will zoom in on it probably closer to about this level with high detail. As you notice, as I zoom in, you'll notice that there is some stars that are blown up around the edges here. If I can get my better telescope, my bigger telescope to image that, I should be able to clear that up. But you can also see there is a lot of other gaseous emissions that are leftovers from, I believe, to be planetary nebula all around this object. So, and as Sandy was speaking earlier about, Sandy, what was it? It was, this is the Crab Nebula, and what was it that you were saying about it?
This is a Crab Nebula. It's a, if you recall, this is the route that a big star goes, and when it dies and it blows up, it becomes a supernova. This one is fascinating. It's been studied for decades because at the center of it is a neutron star, particularly one that's called a pulsar. So it's emitting radio waves that are pulsing something like 30 times a second. We've been picking this up. They first discovered that this was a pulsar in like the 1960s. And if you think of this as a giant star that's down to the size now of Earth, and it's just neutrons, there's no normal matter inside of it. And these are the gases that were blown off when the thing exploded.
Yes, thank you, Sandy. Again, for me, as a photographer, I know less about the technicalities of some of these images than I do just about the amazing beauty that they contain. And this one here was a interesting target for me as well. Also, one of my early successful shots. Eventually, I will go after that one again with my orange telescope, which will capture it much more close up. Now, this is the Crescent Nebula, also known as NGC 6888. Again, you can see that this is surrounded by a lot of gaseous nebulosity around here. This entire area that the Crescent Nebula resides in is very full of gases, and they range in definitely across the spectrum from visible light to your hydrogen and your oxygen and your sulfurs. This particular image, I am trying to remember, I believe I captured this in hydrogen and oxygen. So there's really only two colors here. I duplicated the oxygen as a third color to give it that RGB spectrum. Sometimes certain astronomers that I see on, or astrophotographers that I know online, are particularly good at capturing all of this dust out here and really just giving an amazing contrast to the object itself versus this wispy dust stuff out here. And it really gets quite stunning when they do that. This is the California Nebula. NGC 1499. And this is a fairly large object in the sky, especially considering that I'm using a wide field telescope to image this. And obviously I was not able to capture the entire thing. Some people will go ahead and take mosaics of this using the top section and the bottom section imaged independently. And this is entirely imaged in hydrogen alpha only. So there is, I don't believe hydrogen alpha is particularly visible to the human eye. There's a possibility that you may get a hint of it, but it's very, very dim. But using the filter and the camera, we are able to capture that. And as you can see, due to the shape of it, the name of it, the California Nebula, is kind of obvious. So, and this one is also located near Cassiopeia. This and the next image, this is called the Heart Nebula, and it is its technical name is IC 1805. And this is captured in hydrogen, sulfur, and oxygen. And I list it off in that way because when we create color images out of light that we cannot see, one of the things that we have to ask ourselves is what are we going to choose to name each one of these colors? And in this case, I stepped off of the normal. Normally, the Hubble palette, which is just basically created by NASA for the Hubble telescope, is going to assign some of these colors their own spectrums, such as sulfur would be red, oxygen would be green, and hydrogen alpha would be blue. However, in this image, I chose to change that arrangement to be hydrogen as red, sulfur as green, and oxygen as blue. And primarily I did that because I thought that it was kind of light on oxygen data, and I really liked the way that the colors blended well. So these are all have to be taken with a little bit of a grain of salt, meaning that there is a mix of science and art here. So these colors are really my own rendition. And then this image, which is right next door to the Heart Nebula, is called the Soul Nebula, or Westerhout 5 is the standard name for it, or LBN 667. This is typically made up of the same type of gases as the previous image, but on this one, I did choose to use the Hubble palette. No particular reason, I just wanted to get a sense more of what it was going to look like in that area. And as you can tell along the way, as we're looking at these images, deep space, nebula, and primarily nebulosity is the main focus of what I go for. I am interested in all the other objects as well as planetary photography, but it does require using a different approach and different cameras to achieve those results. So nebulas are my focus. Now this is the Helix Nebula, NGC 7293. And this, like the Crab Nebula, if I'm correct, Sandy, this is a planetary nebula. It is an exploded star, which you can see in the very center of it. As much as this image is a relatively decent representation of the Helix Nebula, there is actually a lot of dimmer nebulosity that occurs out in the outer extremities that I was not able to capture at this time. This image was taken through my my 8-inch telescope up close, and that tends to cut down on the amount of light that hits my camera chip. And so it wasn't as sensitive on there. It's really about I think the only image that I have to demonstrate through the 8-inch scope. The smaller scope generally does a better job for the majority of objects, but it's still a beautiful target. I like to look at it as the eye of God. Some people call it the eye of Sauron from The Lord of the Rings, but it's a very beautiful object. This is the Orion Nebula. And there was another, one of the images that Sandy was showing earlier of the Orion Nebula. This is located in the Orion's, the belt, I'm sorry, the sword of Orion. And there is actually a lot more nebulosity around this, particularly over here where my mouse is going. If we were to see a little further over to the right, you would also have the Running Man, which is a small nebula region that is almost attached to M42. And that is the M43 that Sandy was referring to as the second Messier number that is associated with it. And it is, the two together are beautiful objects, but I typically just go after the primary Orion Nebula. So, and I personally, I just love this image. It's really hard to not get blown out in the center core here, because this area right here is a massive star forming region that is, there's so much energy in that center core right there that any of our long exposures that we try to get with that tend to capture too much of the light. But you have to use long exposures to get this wispy areas out on the outer edges. This is the Jellyfish Nebula. And again, this is a one part of a large area of nebulosity. I am not entirely sure where this fits in with the types of nebula that Sandy was showing us earlier. But it is an absolutely fascinating image because, to me, because of this wispiness that you see coming out of it on the bottom left here. And if you were to see the more full image that would include all of this, it appears that whatever was in the middle of this that blew out, I'm assuming a star at some point, appeared to blow a large amount of material off into this direction right here, which is very fascinating and kind of eerie looking to capture that. And I can't remember what filters I used on this. I believe this is probably a combination of hydrogen, oxygen, and sulfur. Very few of these that I do are actually in RGB. However, the Orion Nebula, that is an RGB image, so that is actually visible light, what the camera would pick up, as well as the Andromeda Galaxy that you saw at first. So this is, none of this is in visible light in here. Now this was a fun one for me because years ago when I first started doing astrophotography, I saw the Horsehead Nebula as the ultimate peak of achievement. The challenge with this is that at no point with the naked eye are you able to view this. And so back in the day when I was not using computers to find my objects, I simply had to take long exposures over and over and over again until there was a trace of it. And then I would hope that I could center that trace. And I was able to a time or two back then, but the resolution that I achieved was relatively poor, especially when I look back. This was my first chance of walking out to the observatory, and I saw that Orion was up, and I knew I was finished with all my imaging for the night, but I was like, hey, you know what? Let's see what happens if I just take one 10-minute exposure with my hydrogen alpha filter on the Horsehead Nebula. And this is what came out of that. Normally, all of the other images that you see are stacked images combining data. This is simply one 10-minute exposure, not stretched, in hydrogen alpha. Now, normally, as I told you earlier, that my camera takes images in black and white. there is an ability within Photoshop to colorize a black and white. This is basically a hydrogen alpha colorization plugin in Photoshop that gives me a red tinge to my hydrogen alpha. So something I was very pleased with. Obviously, we can see the Horsehead Nebula itself here, but the swaths of dust coming up from here, as well as these pillars that are in the back areas here, the more you look at the image, the more other things begin to jump out at it, including this is the Flame Nebula right here. And this large star is Alnitak, or Alnitak. I don't know how you say it really, but I call it Alnitak. That is the lowest leftmost star in the belt of Orion. So, and then as you go down in the image here, you can also start to make out some interesting dust areas back here as well. The amazing thing to me about a lot of this, and particularly with the Horsehead itself, is that these are dust clouds that are very thick and in front of the objects that we see, the clouds that we see in the back. So any illumination that they have is rear illuminated, so giving this dark cloud to the front of it. And it just, as you can see, gives an astounding image, one that I'm fairly proud of. About a week later, when I had another sky opportunity, I decided to add some additional color information to that. So I went ahead and took several more hydrogen alpha images and added some oxygen and some sulfur to it, and coming up with this color image as a result. Technically, my goal was a bit different than where this ended up. I would have liked to have seen all this cloudy formation in here brought to more of a white, and that would have produced, I think, a lot more contrast between the darker objects and the wispiness in the background. This is also an aggressive star-forming region. In fact, the entire Orion constellation, the entire area around it is massive star-forming region. So moving on, this was a bugger of a shot. It doesn't look like that much, and I really don't go after galaxies a lot. I love it when they're good. This one here was very difficult to get, and I was never happy with the results. And the reason why that is because I was capturing this during full or almost full moon. And every night when this is several nights worth of images in red, green, and blue, which is a horrible light bands to capture during a full moon. But I decided to process it anyways and see what I got. This is the Triangulum Galaxy. It is M33 in the Messier catalog.
Yeah, could I interject something here again real quick?
I'm sorry, Sandy, will you say that one more time?
Yeah, can I interject something here real quick?
Yes.
So the Triangulum Galaxy is what we call a dwarf. Well, this one isn't so much of a dwarf, but it's not that far away from us, the Milky Way. It shows up great here, but I have really myself only seen it a few times because it's actually quite dim.
Very dim.
If you remember a few months ago, we had a power outage up here in Ponderay County.
Mm-hmm.
That was practically, I think, county-wide, and it lasted quite a while. Mike, I rushed up to Indian Creek Community Forest when it got to be after dark and went up there specifically to look at this thing with binoculars. And so for the first time since all the years I've been going up that bench area looking at things, I wanted to see this one because it's got a very low visibility surface brightness. And it looks great in this photo, but this is a great example of one that you can barely see even with binoculars. And it's so large that looking at it through a telescope, it doesn't show up well either unless you use extremely low power on it. So yeah, just funny trips that astronomers go on, about these objects that they're trying to see or find. But anyway, sorry about that. I just had to get that in.
To me, that was, even though the image itself is not highly detailed, it was the difficulty of the capture that was important to me on this one, because it was such a super dim object on a moonlit night, and which is the worst time for me to capture anything in visible light. Now, an interesting note on that is that the hydrogen alpha in particular is almost completely unaffected by moonlight. And so when the moon is out, which it seems like it's out every time the sky's clear for me lately, that pretty much just leaves me hydrogen alpha and or other narrow bands, which are going to be your oxygen 3 and your sulfur 2 as well. So I think I have one more image, and this one is the latest image that I took, which was also taken, this was narrowband only. This is the Rosette Nebula, or NGC 2246. This is also the first time that I decided to dramatically extend my imaging time on an object. And this thing, I have a grand total of 18 hours captured in primarily hydrogen alpha and oxygen. I don't think I ever put any sulfur information in there at all. But I used what is called pixel math to create a 3-color image out of 2 colors. And this is basically located, when I look at the sky and I find Orion, I look north from Betelgeuse, roughly. And I'll admit I use computers to track this stuff down, but north of Betelgeuse, about halfway to the point of the next brightest star. And the Rosette Nebula sits right in that area. And the longer capture allowed me to capture a lot of this dark dust lanes that are in here. This is something that I will also be adding data to over the next few years, because it's an object that I'm very fascinated with. The depth in it, the different layers of colors and scale, to me were really fascinating. And so that kind of wraps up the majority of the images that I was going to show you. I also did pull up a single image of the comet that I wanted to show you guys as well. And let me see here, I just pulled that up right here, there it is. And that is Comet Neowise, taken from my backyard, not the observatory, but close. The observatory is actually technically right below it. And as you can see, if you zoom in on it, the 20-second exposures is what gave this an elongated core here. And you'll notice all the stars around it are elongated as well. So because I did not use any tracking mount, it was just my DSLR with a 20-second exposure. And that kind of wraps me up.
Okay. Thank you, Wade. Great pictures. Okay. What I had on the agenda, but we're running long here, so let me take kind of a temperature here. Would you like to stop for some questions? What I had planned was what you can do and get in the way of getting information on looking up at the sky, and not as technical as what we've gone into now. I don't know if you have time to get into that, or if you would just really like to wrap up with questions. So let me know what you think. And I think everybody's able to unmute themselves as they wish.
I am happy to answer any questions about the images or the observatory.
Wade, I have two dumb questions. What are the Starlink satellites going to do to your profession or your occupation?
Well, I will tell you that it will cause me to throw out a lot of otherwise usable frames. Because I am stacking images, and especially when I'm taking very long exposures, I'm looking at large chunks of lost data. The shorter exposures are not so much affected because if I'm taking, say 2-minute exposures, and I'm taking 50 of them, if a Starlink goes through one of those images, it's really not that big a deal to toss one of them. But if I'm taking 10-minute exposures or 20-minute exposures, one lost image is a lot of lost data. So the Starlink does affect me. However, being a fan of space travel and space technology, personally, I'm willing to accept the loss of data for that purpose. I do see other people out there who are complaining in a much larger fashion than I do. But personally, I'm all game for Starlink.
I'm not sure everybody understands what he's talking about with Starlink data. Would you just briefly let them know? We're talking about some satellites that are being put up by Elon Musk.
Yes. Starlink is basically a constellation of satellites that is being put into space by Elon Musk from SpaceX. And his goal is to, I can't remember how many, but thousands of these things. Now, right now, we are at several hundred in space. And so right now, I might not be complaining because what happens is, these things, as they go through travel through in orbit, they tumble, and those surfaces on the satellite are reflective. And so as they move through space, they may cross path with whatever I'm imaging and leave. Because I'm taking a long exposure, I'll see that satellite or a series of satellites as streaks across my image. Now, at this stage, like I said, there's several hundred of them, but there's supposed to be several thousands of them. And it may become dramatically more of a problem as that grows. I do know that they are changing the surfaces of the satellites right now right now they've got them dialed down to about 30% of the visibility